Welcome to the tutorial of lesson 3 about logic gates and digital circuits. You got an exercise sheet with some tasks, and today we want to do the solutions so that you see how I did my work with this stuff here. So let's go to the first task. Use the DeMorgan Law to replace an OR gate with AND and NOT. Use Logisim to simulate all states to show that this replacement is correct. If you remember, we did the same stuff with an AND gate, so that you replaced the AND gate with OR and NOT. So we do exactly the same. So let's first of all create this DeMorgan Law for the OR gate. So what we do is we set the OR. So this means A or B. And this is A or B. And if we do this DeMorgan Law, then we do nothing more than a double negation. So it's the same term. And then we run this DeMorgan Law. So A and B, and then we have to negate both of them, and we keep the other one. So if you watch this here for this part, we use this DeMorgan Law, and then we can replace an OR with this setup. So let's see if the result is really the same. First of all, we draw an OR gate. So we set to 2 inputs, what we had. So then we set 2 inputs. And we have 1 output here. So we combine so that we have the connections and we have the output. So let's test it. 0, 0 is 0. 1, 0 is 1. 0, 1 is 1, and both are also 1. So you have the classic OR gate. And now remember what we did. So we replace it with an AND gate. So we set an AND gate. Also set the inputs to 2. We have another output so that we see the result. We connect the output to the AND, but we should not miss that we have now a NOT here. So the complete output is negated. Remember, we have 1 negation over the whole term. And then we have also each input negated, so that we have a NOT in front of each input. And then we can directly connect to these inputs. So, and if we test it, we should see at the output here the same behavior. So 0, 0, both are 0. 1, 0, both are 1. 0, 1, both are 1. 1, 1, both are 1. So this and this are equivalent circuits. This means that we have a real replacement, and this follows the DeMorgan Law. Let's come to question number 2. So question number 2 asks for additional gates, which are combinations of the basic already known gates. Important gates are also NAND, not AND, NOR, not OR, and exclusive OR. In the exclusive OR, you have the situation that either one of the inputs must be 1 and the other 0, and not both are 1, so that you get that the output the 1. Create the truth tables and draw these gates with Logisim to simulate the truth table states. So let's first of all create the truth table. The truth table for our NAND looks like this. So let's first of all start with the AND gate. So we have 2 inputs, A and B, and we have 1 output, which is the AND. So if we have 2 inputs, we can exactly make 4 different possibilities. So, and then we just change 0, 1, 0, 1 to get all of the solutions 0, 0, 1, 1. And then the end looks like this. So the not end then looks like this. 0, 1, 1, 1. So now we can just follow what we have done with the disjunctive normal form. So for each of the lines where we have a 1 in the output, we create our terms. So B naught and A naught, B naught and A, B and A naught. And we combine all of them with OR, so that we can now use this for a simplification with a Karnaugh-Weitz diagram. So we have all of the 4 possibilities in this diagram, B, B naught, and then we fill. So this position is A naught B, so A naught B is this. Then we have B naught A, B naught A, and we have A naught and B naught. So it's this. In this case, we cannot create blocks with 4 elements, but we can start with blocks with 2 elements. So these are the 2 blocks, and there we just check which parts participate. So we have B here, we have B naught here, and we have A naught here. So remembering the Karnaugh-Weitz diagrams, we delete or cancel the elements which exist with not and not, so that we have the non-negated and the negated form inside of such a block. So in this case, B naught, and then we have A and A naught inside here. So we delete A and A naught, and we combine these both with an OR, so that the resulting part will be A naught or B naught. So, and this we can now draw with the Logisim. So first of all, let's set the 2 inputs. So we do a change of the facing, so that the connection point is in the south, and a second input, the same, 2000. So you have the connection point here now in the south, because we need a little bit of connectivity. We want to show all of the different NAND solutions here in this case. Then we directly fetch the NAND so that we see how the result should look like. So we have a predefined NAND here. So it's an AND and a NOT. So we combine this so that we have A and B, and we have an output here. So let's test. Both are 0. Remember, should be on. If one or the other is 1, then the output is 1, and if both are on, then the output is off. So it's exactly the same as if you do this. Because it's nothing more than what the NAND does. Okay. So we created the NAND with AND and NOT. So following the truth table, we had the situation that we have 3 different terms. So we take 2, make maybe another size so that we have it a little bit smaller. Then we copy and paste the same stuff. So do you remember we had 3 terms, and then we now connect the terms according to what we saw. Let's jump back. So we have not 1 and 1 not. Okay, So let's jump back to the sample. So we have not not, so we need two knots here. Let's also go to the other side. So not not, and either one or the other is not. And then we do the connection. So first of all this and this. Let's connect to here. So that we have the connection points. And then we combine everything with an OR, with 3 inputs in this case. And then let's connect the output from here as input of the OR, and this is our new output. So this was the original truth table as we got it. So let's test if everything works. So 0 0, or either this, and only if both are on, then you have a not. So it's exactly the same, you see. And now let's do the reduced form, which we created from the Canova diagram. So let's jump to this. So what did we have here? A not or B not. So let's do this. A not or B not. So we need an OR with 2 inputs. And then we have 2 nots. Which you connect. And we have an additional output. So if everything works correctly, then the output should be exactly the same for all situations. So you see, we have created 4 different versions of the NAND gate. So if you compare now the first and the last of these solutions, so maybe you directly see how the conversion can happen, because it's nothing more than the DeMorgan's law again. Let's take the last solution, or those one which we created here. So we have A not or B not. So and if we do the DeMorgan law again, then we can make the following: A not or B not, and we do a double negation over the whole block. And what happens then? We then apply the DeMorgan law. So we have A not not and B not not, and completely negated, and therefore these can be cancelled again, so that we have A and B not. So, and if you compare this, is this solution, and this is the solution of the first part. So if I switch back, you directly see this. This is the solution with the negated inputs and an OR, and this is the solution with an and a negation or a not at the output. And the conversion between both is the DeMorgan law. And now we can continue with the NOR and do exact the same. We create the truth table. So in this case, again, we have 2 inputs, A and B. We write the output for OR, and then the output for NOR. So again, 4 different possibilities. So So in this case, we have 0, 1, 0, 1. We have 0, 0, 1, 1. And the OR is this. You remember? And then we have the NOR, which is 1, 0, 0, 0. So in this case, it's quite simple. We can create, for this line, the adequate setup so that we have a NOT and B NOT. And this is the circuit for the NOR. So let's draw this. Again, let's start with the NOR so that we see what should be the result with 2 inputs and 1 output. So let's connect this. And then we connect the input and then we can test. So it's just 1 if both are 0. And with our solution, we can do the same. So we have an and we have NOTs at the input. So let's put the AND with 2 inputs. So if you create this, you can have the same style again, where the connection is nothing more than the DeMorgan Law. New output. So if you just look onto this, if we test it, so we set, you have exactly this behavior. So the conversion between these two things are defined by the DeMorgan Law. And finally, we do the same with the XOR. So let's paint the truth table. So we have the inputs A and B, and we have the XOR output. So in this case, XOR means that we will have just a 1 if either this input or this input is 1 and not both. So we will have just this part here. So we have 0, 1, 0, 1, 0, 0, 1, 1, and then we have this output. So going to the disjunctive normal form, we have then A and B not, or A not and B. So this is the XOR part, and in this case we cannot do a simplification, because if I draw the Karnaugh-Weitz diagram, so if we do it in the same style, A not, B not, and then if you watch the ones, so we have a 1 at the B not and A. B not is this line and A is here, and at the A not and B, A not and B. So we can not make any blocks combining the things, and therefore we cannot simplify this. So let's draw the solution in the circuits. So we create a new line, that we have it available here, and then we can continue with the same stuff here. And first of all, we take the XOR from the selection so that we can compare if we made everything correct. So we have a new output. We connect the outputs and we connect the input. And then we do our own creation where we had A and B not. So and two outputs and maybe smaller size. So, and then we need one NOT for the B. And then we have another AND where we negate the A input. And we combine all with OR with two inputs. And we create one output. So, and let's have a look now if both of these output reacted the same way. So we have 0, 0, we have a 0. If one of this is 1, then we will have an output of 1. And if both of these inputs are 1, then we have an output of 0. So here is the XOR. This was the NAND, this was the NOR, this was the XOR. So let's come to question number 3. So question 3 is now a real application of what we know. So we use a real conversion between different representations of numbers, and we want to do a real logic and electronic gate or circuit which does the work for us. So the idea is that we use a so-called 7-segment display. In this case, you have 7 LEDs which are arranged to represent a number. So let's first of all read the lesson. The simplification of logic gates from the lecture is also used when an electrical conversion between representations of numbers must be done. In the following task, we want to convert the binary number from 0 to 9 to a single 7-segment display with the segments ABC to G, like in this figure here. So each segment is an LED which can be turned on and off. So therefore you can define own truth tables for each segment which converts the binary representation with 4 bits to the corresponding LED state of the 7 segments. So each truth table can be used to create a disjunctive normal form and to simplify it to get a minimum of gates with this kind of Weich diagram. So you can now do the organization with your colleagues so that you don't have to do all of these things. You can also solve the circuit for the whole 7-segment display so that you set the input bits and you get the output LED. So what I want to show you first is a sample how this LED will look like. So I created an Excel table. So where you see here is 7-segment display with A, B, C, D, E, F, G. And I can set here numbers. So 0, for example, switches on these LEDs. 1 is this. 2 is this. 3 is this. 4 is this. 5 is this. 6 is this. 7 and 8 and 9. Okay, so you have here the representation in the 7-segment display, and what you can now do is you can have a look onto each of this different segment, and you can make a truth table. So you have 4 inputs to represent the numbers up to 9, from 0 to 9. You need at least 4 inputs. So 0, 0, 0, 0 is 0 in decimal. It will light the LEDs in this way, and then you can check which of the LEDs is on, which is then an output table. So you have 7 truth tables in one here. So 4 inputs, and the first output is A, first truth table, the second one is B, and so on, so that you can do a simplification for each of these truth tables. This means in any case, for example, for the A, you will have this situation, and then you can create a kind of wedge diagram, and then you can find the blocks. So for example, in this case, here is one block, here is one block, here is one block, and here is one block. There would be another one like this, but the elements are already part of a block. So I can select, for example, the B truth table, which checks the states for the B LED. Then you would have this one, or for C, and so on. So you can create own simplifications, and then you will get this output. So in Logisim, you already have such a 7-segment display, and you can set different inputs, for example. So if you do this input to here, for example, and you switch it on, then you see this is this line in the middle. So if you go to the next one, it's this line. If you go to the next one, it's this line, and so on. So you have different inputs. In this case, you have even 8 inputs, because it also represents the dot. You see, here's a dot, so that you can also switch on the dot. We don't use it in our situation. What I want to show you is now a complete setup for the whole 7-segment display, and also for the complete set, which can be represented with 4 inputs, so that we have 2 7-segment displays which represent exactly the whole number. To have some control, I have here also another output, which is a hexadecimal display, which is also supported by Logisim, so that I can check if this number is really represented here in a decimal representation. So let's do the input. So 0, 0, 0 means 0. So if we switch on 1, we have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And you see it's a complete set of the numbers, and you find these 7-segment displays in real world, for example in watches or other representations of numbers, because it's a very simple way to show decimal numbers to customers or users of a device. So therefore it's a quite nice sample, and maybe you can also use it for your own projects. Let's go back to the next question. So the next question is question number 4. Use your truth table from question 3 to also create the conjunctive normal form. So if we have a look now again onto our truth tables, for example from this Excel sheet here, then the disjunctive form takes always the lines where we have a 1. So now we want the conjunctive form, so now we take the lines where we have the zeros. So therefore, let's do this. So what we now do is we create the truth table again. So in this case, we have 3 input A, B, C, D, so that it looks like what we know, and we have 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Here 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, which is in decimal 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we don't take care on this part here. And then we have 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, and we have 0, 0, 0, 0, 0, 0, 0, 0, so 8 times 1, 1. So the disjunctive normal form would look into the part where we have the ones in the binary representation. So if we look into the section A, so the LED A is represented in this way. So if we watch, for example, our 7-segment display, it would look like this. And LED A is this one in our representation. So for 1 it's this, for 2 it's this, for 3 it's this, and for 4, and so on. So in this case it would be on, in this case it would be off, in this case it would be on, would be off, so that we can create a table for 5, 6, 7, 8, and 9. So this would be the output for LED A. And now the disjunctive normal form would look onto the one. So this one would be in the disjunctive, and this, and this, and this, and this. And the conjunctive normal form just looks at the lines where the output is 0. And then we use the positions here where we have a 0 non-negated. So we would have here A, and now we have not N, we have now OR here in this part, A or B or C, or, and D is now a 1. So in the conjunctive normal form we use this then in a negated form, and you combine all with an AND. And then we have the next one, which is this. So it's A or B not or C or D. So, and this is the solution in conjunctive normal form. And therefore let's play again with our Logisim. So we create a new connection possibility. So we take the inputs and draw the lines up here. So here are now the inputs again, like from the origin. And then we can draw here the combination. So what we have is A or B or C or D not. So we take a OR with 4 inputs, and we just connect the rightest part is the D, and then we have another OR connection with 4 elements, and where we negate the B. So we negate the B. And the output is combined with an AND with two inputs. So and this output should now be the same output like this here. So therefore let's test it. We take the 7-segment display and we connect it to the correct output. So in this case it's this output. So now if we change our input again, now we should see that this number is exactly the same. So it's off, it's on, for 3 it's on, for 4 it's off, for 5 it's on, for 6 it's on, for 7 it's on, for 8 it's on, and for 9 it's on. So now we have created the same output in a conjunctive normal form. Let's jump to the next question. So the next question creates other more complex structures for our circuits, so that not only flip-flops and adders are in our mind, also other more difficult or complex structures. So not only adders or flip-flops are important for a calculator. Another often used circuit is a multiplexer. It uses a different number of input lines which are routed to one single output line using a corresponding number of control lines. For example, 4 input lines can be selected with a 2-bit control word. Create a circuit, draw it with Logisim and test it. So the idea is now that you have, for example, 4 lines which you want to send to one line where you want to send the data. And then you have to multiplex. So you send the first bit, you send the second bit, the third bit, the fourth bit, and then you continue again. So that you always send bits sequentially over a line. And on the other hand, you have a demultiplexer where this one line appears, and then the first bit goes to this, the second bit goes to this, the third bit goes to this, and the fourth bit goes to this. So this is a multiplexer. And we want now to create this multiplexer. In principle, we just need our truth table again so that we can do this. So let's directly jump to our simulation tool. So we have 4 inputs. Therefore, we want to create 4 inputs. Let's do the south direction. I copy this, that I have 4 inputs. And these 4 inputs should go into my multiplexer. And additionally, I have a selection line or a control word which selects according to the setting, selects the first line. So 0, 0 selects the first line, 1, 0 selects the second line, 0, 1 selects the third line, and 1, 1 the fourth line. So what we have here, we have a truth table, and therefore we can just do the following. We put an AND here so that we get the first line. We have 3 inputs. And we do 0, 0. So this means we do 2 negations here, because this is the first of our truth table. And then we select the first line. So the next one is the 0, 1. So we have this negated. So we take this again, and this. And select the next line. So if this is true, and here is also a true value or a false value, it will select this part here. Then, third line in our truth table is this one. And we select this one. And then the fourth one is all are true. And when we connect everything with OR, so we have 4 inputs here, and we connect 4 inputs to this output. So this is our output line, our single output line, which I just represent with a output pin. So this and this and this. So, and now with 0, 0, I select this pin, so I can test it. So if I switch this, it arrives in the output. I can switch the others, which will not have any effect. So if I switch this on, this will not appear, but this will appear at the output. So I select the second line. So you see, if I switch on this, I select this line, so I can change this. If I change this, it will appear in the output, and all of the others are not influenced. And only if I have both selected, I will select the fourth line. So it means with this control address or control word, I address the other 4 input pins, so that only those value is sent to the output which I have selected with my address here. So, and therefore I can do addressing, or I can do a multiplexing, so that I send over one single line according to this setup. So for example, if I have a clock pulse, I can switch between the 4 different bits, and if the receiver receives it in the same way, it can also select the right position and rearranges it with a demultiplexer, for example. So therefore I can have a mechanism to sequentialize bits, or I can have a mechanism to address bits. This is quite important for calculation machines. Let's go to question number 6. Question number 6 is about additions and an adder. So we learned about the full adder in the lesson. Create a Logisim board which adds 2 8-bit numbers. The sample for a 4-bit adder is in the slides. Show the input and output numbers on a hex display, and think about lower significant bit and most significant bit, and carry over scenarios. So let's switch to our Logisim again. Here you have the sample for a 4-bit adder which you have in the slides. So what it does is, if you set this, then you will get the addition. So for example, if we have 2 and 1, which is 3, plus 1 is 4. Or if we add 3 plus 3 is 6. So here's the lowest significant bit here and the most significant bit here. In principle, what we have to do is now just we have to double this equipment, and this I have directly prepared here. So we have byte A and byte B. And now you can set 8 bits for each byte, and you do exactly the same. And you have to define the least significant bits so that you always add the correct bits to each other. So least significant bit and least significant bit of the second byte. So, and then the principle is the same. So you have as input, you have no carryover, and as output, you have the carryover. So if you cannot represent it anymore with your numbers, so if you have a carryover at the last position, then you will have a LED which shows that the type is overflowed. So let's do it. Should do exactly the same. So if we define byte A with 3 and byte B with 4, then we should get 4 plus 3 is 7. So, and if we want to produce, for example, 8 plus 3, then we will have 11, which is B here. Okay, so it works quite well. Now we can produce the carryover, for example. If we cannot represent it anymore, so if it is more than what we have available, then we will have a carryover, so that the places do not fit anymore for our situation. So this is regular, that we have now a type overflow and that the number is not correct here. So in this case, FF, so complete set ones of bits plus 1 would be or would require a new bit in the higher position here, and therefore we result in 0, 0. And this is exactly this error which you will find if you use the wrong type. So if you have a complete set of bits and you add 1 so that you reach a larger number than what is in the max, then you will have this overflow and you will come back to 0 in this unsigned setup. So let's get to question number 7. Question number 7 is a little bit for experts. So if you want to train a little bit of this stuff, then you can play with it. Quite important is, for example, if you have multiplexers and things like that, you usually need also counters. Therefore, we do this and create a counter. Sophisticated circuits use binary up and down counters. Think about what you would need for counting numbers and select a suitable gate from the lecture to implement the counter. Draw it with a Logisim map and show the counted value with a hex display. So let's think about what do we need. So if you remember the lesson, then you might have an idea of a counter. Counting means you have to remember what was before. So the previous state must be in knowledge. So therefore, you need something like a memory. And if you have in mind memory, then you find in the lesson flip-flops. So for counting numbers, we need flip-flops. And therefore, let's go to our sample here. So here I've drawn some counters which does what we want. So we want to count 4 bits, so therefore we need 4 different memory elements. And the idea is quite simple. In this case, each time if I have a clock pulse, I do the counting event. So if I use the clock directly here, the output is the input of the next, and so on, so that I have a connected sequential count up. And in this case, if I do it in this way, if I just use the output as a clock of the input, what would happen? You will see directly. So I start with 0. If I do the next clock, I get F, E, so I get a down counter. Therefore, it's already a counter and it already remembers the previous state, but what we want is we want an up counter and we want a down counter. And therefore we have to think about when do the different states switch. So the different states always switch if the previous states are 1. So if you remember the truth table, then you have a setup where you can identify this situation. So let's paint the truth table again. So we have 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, so and so on. So if you always look onto this, when the next value rises up to 1, then you have the situation that the previous one is 1, completely filled. And also here, the previous ones are completely filled, and also here. So the previous ones are completely with 1. So you can use this now for your up-down counting. So in the first one, you just connect to the previous state. In the next one, you connect to the both previous states. And in the next one, you connect to the 3 previous states. So where you can use, for example, the situation that you have the previous state already here. So, and therefore, we can go to this counter here. So the first one is we set both to 1, so it means we toggle in a JK flip-flop. The clock now directly goes into the clock. It's not a feedback from the previous one, so we always clock each of our flip-flops, and then the output of the previous one is the input of the next one. And then we take, if both outputs of the previous one are true, so a AND, we take this as the input of the next one, and if all of the 3 previous one, which is a combination of this and this, so the output of here and the outputs of here, then we take this as a toggle input for the next state. So, and then in this case we have now the up counter. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. So now you can think about the down counter. The down counter does not use the output, which is non-negated. We will take the output which is negated then, so that we have down counting. And you see it's the same principle again, so that a synchronous down counter looks like this. So 0, F, E, and so on. Okay? So these are quite important gates. This means that with a multiplexer, with a demultiplexer, with all of this stuff, you have very powerful tools to create your own circuits, and which are always required for high-level hardware. So therefore, we did all of this stuff, and I want to say thank you for listening, and see you in the next lesson. Bye bye.